you very much. I appreciate that. So I'm going to talk a little bit about debugging. And I actually think it's kind of an important topic. Usually, actually, in the little bio that I give, I don't know if I gave it to these guys, I actually add to that, and I wrote my fair share of bugs when I was doing the astrophysics, because I think we all, I think it's worth recognizing that we all do that. Or if you're one of those few people who don't ever write any bugs, I'm sure you have colleagues. So, okay. Anyway, so we're going to talk about debugging because I think we all want our code to be right. I'm going to start off with some observations about kind of the state of the field. I like to do that in my talks, just to sort of level set, and hopefully this will sound a little bit familiar. So I'm definitely coming to this. We were just listening to a very graphics-oriented talk, but I'm definitely coming to this from the HPC compute side of things. So I've been coming to GTC not every year, but most years for a while now. And definitely I felt this year was pretty neat. I was seeing a lot of more variety in the domains of activities that are going on. I really think that was the thing that I really noticed in the talks and in the expo area and the keynotes and things like that. Definitely, aside from the graphics, which has always been a big part of GTC, even the science and the compute that was going on is not just numerical simulations anymore. I think that's pretty neat and pretty cool. Definitely, the maturity of the software stack is continuing to come along. And I'll talk a little bit about that a little bit later in the talk. A lot more users. Definitely seems like Cuda and associated GPU programming technique are becoming more widespread and mainstream. And obviously, that also means maybe some of the really earliest adopters were willing to put up with a fair amount of awkwardness, maybe, and that's, I think as we get broader, we start seeing programming paradigms that try and ease the transition from the host processor in world we're probably all used to the device. There's definitely a variety of programming paradigms. That's something that's been happening for a while, but it seems to be reinforced by what I'm seeing this year. And then, of course, the sort of new thing is open power. And ARM is coming up as a host processor architecture for GPU. I'm going to do a little bit of an aside to explain who RogueWave software is. I guess I can ask. I like to ask questions as I'm giving the talk. So how many people have heard of RogueWave before? Okay, about half the group. Okay, that's cool. We'll talk about challenges. What are some of the challenges that I think are out there in the area of debugging? And then I'm going to focus this talk on techniques and strategies. You can always come to our website, and I'll put it up at the end, or talk to me to get a demo and really learn the actual techniques the actual buttons to push on our tool and things like that. But I think the more interesting thing for a general audience are some of the techniques and some of the strategies that at least I'm hearing people using in this space. So I've got a lot of slides. I'm not going to read all the words on all the slides. I figured that way they'll get recorded, and you can look at them later, or you can contact me, and I'll send you the slides or whatever. So who's RogueWave Software? We're a sort of a software development tool and component shop. Our goal is to simplify complex software development, improve code quality, and shorten cycle times. Those all seem like good things. We have a lot of different technologies. And I'm really focusing on just one of those, the little heartbeat up there, debugging complex code. And I'm the product manager for TotalView. We actually have a whole other product that's within that space called Clockwork. So we have a lot of different capabilities to bring to the table and to help you out with that lofty goal that we presented there before. And I'm really just focusing on one piece of that. But I want to let you know that we do a lot of different things and touch a lot of different code and a lot of different customers. This just shows some of the logos. And one of the things I think is really neat is the breadth and depth of different customers that we work with. So, and actually, TotalView is in a lot of those accounts. So, because everybody's got to debug. It's a very horizontal thing. Okay, so thinking now more specifically about GPUs, this is a short list of the many things that I saw at this show and over years talking to people. And one of the things I think is neat is again, the breadth of this. The physical modeling, that's, I mentioned, came from astronomy, astrophysics. That's where I sort of came from, and I know a lot of GPU code does that. But there's now biological modeling, financial modeling. It's been kind of fun getting to know some of the people that do that and use TotalView. The deep learning, that was sort of a new. I know that it was out there, but that seems to be a big thing this year at this show. Signal processing's been around for a long time, and I could have put a lot of bullets under there, I suppose, in oil and gas. So there's just a lot of stuff going on. Within all those domains, I think there's some really common challenges that make GPU debugging, certainly not impossible, but just a little harder. It's one of the challenges. I was actually talking to someone about an hour ago from a university in Australia, actually, and he was saying that he really feels like there's a lot of people out there who would like to take advantage of GPUs, and one of the barriers that they have to entry is that, what if something happens? It's hard enough to write the code, but then what if something happens? How do I figure out what's going on? So what are some of the reasons that GPU debugging is hard? I think part of it's really wrapping your brain around the hardware differences. You have to do that to write Cuda to begin with, but then to really troubleshoot it, it feels like you almost have to. Well, there's the old adage that debugging code is what is it that Kernighan or Ritchie, one of the others, said is 10 times or 5 times harder than writing code to begin with. So you have it kind of applies to the hardware differences. You have to understand what's going on, maybe at a finer grain, to troubleshoot. There's data decomposition. It's all. I think it's one of the things that we're trying to do in the Cuda space and in the OpenACC space and OpenMP space is make it a little easier, but you still have to fundamentally map your data and your problem onto a very specific device model, and in the form of arrays and grids. You have to worry about data transfers explicitly, and you have to think about what are the potential race conditions at the edges and communication at the edges. Buffer overruns, because you're doing all these data transfers, because you're working in a different address space, there's all kinds of opportunities for, you're doing a lot of code that's just moving bits around, and every one of those is an opportunity for a buffer overrun. Pointers, complex enough, daunting that, we all use them, we have to, but they're a point where you can potentially do crazy, awful things to your program, and we're doing them now in different memory spaces. You have to pay attention. It's just another thing you have to pay attention to. Concurrency and parallelism, of course, there's very few things as parallel as a GPU. There's these directive-based languages which seem like potentially a white knight to come in and save you from a lot of this complexity, and they do definitely help. They're definitely a step forward, I think. And we have a couple of them. I got some of the logos up there. You guys probably know about all of these. They take care of some of the data migration for you, which is a fantastic thing. But there are still some challenges. They're not a silver bullet. They don't make debugging unnecessary, but they certainly do help. So the fundamental things of like the needle in the haystack, the fact that your computation is happening in lots of places, and any one error might cause a problem, is still there. Okay, so just some high-level observations. Now we're going to talk a little bit about strategies. And when I started looking at this, there's a lot of debugging strategies here. I think that's actually kind of neat. I mean, I think there's a lot of depth to debugging. There's a lot of sort of passed around informal knowledge in the community. So I think that's actually kind of cool. I think there's some things that we can probably all learn from one another about debugging strategies. So anyways, I started with a high level. This is how I think about debugging, just if I really try to abstract it. This maybe is not a perfect model, and I've not done this presentation many times, so please talk to me afterwards if you think I'm missing part of this or the cycle isn't perfect. But I think you start with your design. I don't think you should wait to debugging until the end. You should think about all the code practices that we all know we're supposed to do. You should really do them. Use reasonable variable names. Think about modularity. Test first development. All that kind of stuff. Document, because you will forget. The thing that seems so obvious now will not be obvious to you 6 months from now. We all know this. Capture what you need to reproduce a bug. When a bug comes in, whether it's from testing, whether it's from you or a colleague reporting it, or from the field, these are all the things you have to think about. It's not trivial. Then we get into the stage. Once you have that, once you can reproduce the bug, then you have to localize the bug. Or I'm trying to be a little precise with the terminology here, the symptoms. Where does this first go off the rails? Then you start into a hypothesis testing cycle, iterating. Is this sounding familiar? This is all crazy talk, or is this kind of how you approach bugs? Okay, I'm seeing some nods. That's good. Then there's the fix. Hopefully you get to that stage. And then there's validating the fix. And I think all of these things are part of the sort of cycle of debugging. Anatomy of a bug. I want to not actually talk about real bugs, but talk about the anatomy of a software bug. And so I was thinking about this, and I'm starting to kind of evolve a little bit more formal language about this. And I think think it's worth thinking about what are all the pieces that go into a bug. I think there's a citing. You know, what is it that told you there was a bug? There's the defect itself. That's the cause of the bug. Then there's the effect of the bug. And that could be, you know, whatever it is that happens because of the bug. And it's actually kind of an interesting question. If there's a bug that changes the state of something and then that state's never used in the program, is it really a bug? I don't know. Kind of like if a tree falls in the... Anyways, so the incorrect state that gets out to the outside, the error propagating through, or the visible behavior output hanging, crashing. You know, we know all these. There's a trigger. What are the input conditions that cause the defect? Because it doesn't happen all the time. Just because there's a defect doesn't mean you're going to get an effect, right? Everyone understands that, right? We could have a buggy code, and then we could have input that doesn't take you down the path that gets anywhere near the bug. Or the bug happens when you're at an order of 2 size in your array, and once you put in something that's not a factor of 2. You thought it was always going to be a factor of 2, but somebody comes along and puts in some data that doesn't, you know, isn't power of 2. Then there's the reproducer. That's kind of the articulation of what you saw that includes the trigger condition. And this I find in actually dealing with bugs. And again, I'd love some feedback here from you guys if you agree. This getting to the reproducer is actually sometimes the hard part, right? You know, maybe it gets a little simpler after that. And there's the resolution, obviously, whatever it is that you do to fix it. Verifying to make sure that you actually have fixed it. And I think a bug is all of those. So the kind of the point of this slide is here, I think everything above the line that says a bug is what the bug is. The bug isn't just the defect. It's all the stuff that you have to do to understand the defect, what the defect does. All of that, I think, is the bug. And then, because I sometimes find myself talking about, well, getting back to the root cause of the bug. Well, what is really the root cause? And actually in putting together the slide, I think I changed my opinion. I was kind of had been talking as if the defect itself was the root cause. But it's not really. I think that in some cases, it's really valid to push the root cause back to, well, why did you think to write that? You know, was it just a mistake, or was there actually a misunderstanding? And I would argue if it's a misunderstanding or an architecture that wasn't right, that's actually the root cause. So, but I don't know if it's part of the bug. Yeah, maybe it should be above the line there. Anyways, so if you guys have feedback on that anatomy of a bug, I'd love to hear that actually, because I think it'd be nice to have an articulation of all the pieces. Okay, so some observations about So I'm going to get to GPU debugging, but I'm going to take a route through some of the actually slightly simpler cases, because I think a lot of the techniques apply. So I'm going to start with multi-thread debugging. I think multi-thread debugging is you know, very easy to underestimate how challenging it is, but it's also easy to overestimate. So it's easy to get a little too afraid of multi-thread debugging. The main thing that's different about multi-threaded debugging is that you've got all this shared memory that any one of the threads can access. So if you compare it to sort of multi-process parallelism, you know, you don't have localized communications. You have the possibility that any part of your program is communicating with other threads. So what are some techniques for multi-threaded debugging? So I think you can do print debugging, but I think I would caution against print debugging in multi-threads because it can change the timing, and you can also get weird interleaved output. You want to look carefully at the multi-thread capabilities. If you're not going to use print statements, you're going to use a debugger. And I've got just some things here that I think you want to look for. I think asynchronicity is really important. You're dealing with an asynchronous problem. You want to make sure that the debugger can allow you to exercise that. You want to have easy access to all the threads. You want to have complete control of them. And I've got some things that you should look for in a debugger. And I think, of course, you want to be able to see what's happening. See the thread state, see the thread private data. So how would you approach a multi-thread problem, even assuming you have a tool that gives you all of this? Well, obviously, the first thing, and it sounds weird to say this, but is try to reproduce it without threads. Obviously, if you can do that, it's simpler. You know, save yourself the trouble, just debug it single-threaded. Vary the number of threads. Why would you want to do that? Anybody got any guesses? Right. I mean, varying that will change the timing fundamentally, and may allow you to find a scale at which the race condition becomes less racy, or something that fails all the time. Something becomes racy that starts to tell you, what might be happening with it. Look at if you have, or if you have a hang or something like that, and also if you get a race condition, look at your synchronization points. Probably, if you have a race condition that's a data race, you should have some mutexes or something like that guarding data. So start looking at the places where you have those, maybe something is not calling the right mutex. It's really easy to copy and paste a mutex and just get the wrong variable name. Use watch points. If you do start to figure out exactly what thing is getting stomped on in a race condition, for example, use watch points. Even if you're trying to understand a bug that isn't a race condition, a watch point is a great way to focus the attention. If you have a lot of different threads that could work, if you have like a work queue or something like that, if you have a lot of threads that could work on a bit of data, you don't have to step through and run each one of the threads. If you just use a watch point. Does everybody know what a watch point is? I mean a data breakpoint, a breakpoint that's triggered by accessing a certain memory location, is a great way to focus your attention on the particular thread you're interested in and kind of ignore all the other threads. Make sure your resources are cleaned up before thread termination. That's just sort of a bit of advice. And then capture the exact execution pattern. So if you have the capability to do record and replay, I'll come back and talk about what that is. That can be a great way, if you have a race condition, to capture that and have that reproducer that I talked about before in a really quick fashion. And I'll come back to the record and replay. Techniques for, okay, so sort of as a sort of building on top of the multi-threaded debugging, now I want to talk about GPUs. And basically everything that I talked about under thread debugging I think applies to GPUs. Right? I mean, there's some hardware differences, but you still have asynchronous, you still have shared memory, you still have the possibility that any part of the, well, on the device, any part of what's happening could be communicating unintentionally a change into another part of the program's memory. Memory is not protected on the GPU, and by that I mean things like seg faults, and there's no isolation of two different processes, memory from one another, so two different things that are happening on the GPU. Well, they may have separate memory spaces, but assuming that you're talking about global memory or device memory, it's all shared. And there's also no checking to see if you're writing out of bounds. So there is a Cuda mem check you can turn on. So basically the hardware doesn't watch for that. You can turn on Cuda mem check, which will slow things down, but you'll suddenly get the basically equivalent of a seg fault if you write out of bounds or read out of bounds. You want to compare data at the host side and the device side. And I'm trying to avoid reading all the words on this slide. Definitely want to look for return values on Cuda malloc and look for return values as you launch or you check your return codes on kernel launches. Vary the domain size. This is just like the thread one before. Vary your domain size, your input data size, because if you have a bug that's lurking and the way that you laid out the data across the device, it's very likely that by changing the input data size, you'll cause that to either occur or not occur, and then again, that'll give you a clue of where that's occurring. I mean, I think it's really easy to write code with making some assumption about the input data size or the input data geometry, and then all of a sudden have that no longer be true. And then obviously look for pointer memory types. Again, that's a new concept that the GPU has that the CPU doesn't. Memory is just memory for the CPU, but for the GPU, you have global memory, you have shared memory, you have private memory for the individual threads. And there is a thread checker capability. It's a cool thing in the Cuda runtime. So if you have a race condition and it's happening on the device, then use that. That's a good way of checking to see if you've got a possible data race. If you have a race condition between the device threads and the host processor, the Cuda memcheck can't check those. So there, what I would encourage you to do is add a little bit more synchronization. You might have taken out the synchronization in order to get speed. Add it back in, turn it back on, see if the problem goes away, and then that starts to give you a clue for what you need to be watching for. And even if you're not putting it in at the hardware level, you can use the debugger to force synchronization. You can kind of just pause one part of the process and run the other part of the process. It's one of the things you want to make sure the debugger lets you do that. So you can either run the CPU ahead or you can run the GPU ahead. Okay, so we also, with TotalView, deal with distributed apps. I'm going to quickly talk about some things for debugging distributed memory applications, clusters here. Again, print debugging, some people will do it, but I think it doesn't really scale, and I've actually done that. Before I started at TotalView, I have to admit I wrote MPI codes and tried to debug it with printf, and so I know how painful that is. I encourage you not to do it. The big problems that you can have distributed apps is the needle in the haystack problem, which I would describe as you can have the error can happen anywhere in the job, And it'll still cause it to be wrong at the end of the day, but you have to kind of look for it everywhere. And then there's also the passing the bad apple problem, which is a little more rare, but even if you run your job and node 16 crashes, it's likely that the error, the actual defect, was on node 16. But it's possible that it was on some other node. You got some bad data, that you passed the bad data to node 16, and then node 16 got around to crashing. That's a little more rare, but it is possible. You can run in separate debuggers and in processes, but I think it's not a good idea. So you should look for parallel debuggers, lightweight debug tools that do these things. And it's a pretty similar list to what we talked about before. Again, you want to have one point of control attached to all the different processes, give you a way to see all of that, give you a way to work with them. Again, the ability to sort of control and set up different scenarios. This shows you want something that will aggregate the data and boil it down for you. And this is showing a cool tool, not TotalView, called STAT, that has been used to debug, I think, over 1 million processes. And what they do is it's giving you a stack trace and condensing it down in a graphical format. So you can see everything is doing the top of the stack, and then down here you have, this is a smaller run, 2,046 processes doing this, and then I have one process doing this and one process doing this. If that's hung, where would I start looking? It's really easy to see that you want to start looking over here. Oh, okay, so I'm actually, oh, now it's telling me yellow. Okay, so I'm going to skip ahead a little bit to techniques for GPU accelerated clusters. Again, you want to try out different relative orders of execution. You want to look for synchronization in MPI, distributed memory programs. You have mutexes for synchronization in multi-threaded applications. You have some synchronization in the Cuda applications. In MPI applications, it's around your communication. So look for assumptions about the way you're doing communication. Okay, we'll skip ahead and past log file debugging and memory debugging, but they'll be there in the slides if you want to look at them. I mentioned reverse debugging before. This is a technique that allows the program, the tool, to record the execution history and then allow you to re-examine that at a later point. And I just think that's super valuable for tracking down race conditions and just for anything where that defect and then the effect and then the sort of symptom are widely separated. It's really helpful to be able to start with the symptom and then work your way back to the cause. Not going to talk about that one. I'll skip ahead. So Corefiles, I mentioned Corefiles in the title of this because that's actually one of the new things in Cuda 7, which was just released a couple of days ago, is the ability to generate Corefiles. And you might think, since I'm an advocate of interactive using a debugger and a debugging tool, that I would scoff at Corefiles, but I totally don't. Corefiles are really handy. If you can get a program to crash and get a sense for where that is, you skipped ahead through the first couple of steps of the debugging scenario because you figured out at least you can get to the symptom and you can get at least part of the reproducer pretty quickly. So anyways, I mentioned some of the commands you need to turn on Corefiles in Cuda so that you can get a device a Corefile. So definitely encourage you to make sure, that's a new capability in Cuda 7, and I think it's a really valuable and helpful one. Batch mode debugging, I'm going to skip just because I saw a warning color back there. So just a quick review of some of the tools that are available. You probably want to be aware of all of these. Obviously, there's print statements, Cuda memcheck. Definitely don't skip that. That's a really cool thing. There's Cuda GDB. There's Alinea. There's Eclipse Insight, TotalView. And actually, someone was reminding me that there's also the Larry, help me out. What was the name of the other tool? We were talking to somebody. Yeah, it was Concurrence Computing's NIGHT, something like that, debugger. NightView? NightView, thank you. NightView debugger. So check out all of those. So TotalView is the one that I product manage, but I'm trying to avoid pitching it too much in this talk. It does almost all the things that I talked about here, in particular all that stuff about giving you the ability to set up different thread sequences and multi-process sequences is like the core bread and butter for TotalView. Of course, it includes GPU capability. And for example, you have, in this case, we are working in a kernel that's been launched You can see you have your host side thread there, and you have your device thread. You can work your way through all the different permutations of the thread. You can switch back and forth. You can look at data before it's been sent, look at see how it's looking in the device, and you have complete control of those two things. So we talked about doing some synchronization in the debugger. That's all possible here. This is just sort of a quick endorsement from a customer. They had been not using TotalView and trying to debug a parallel GPU accelerated application the hard way, and they were just stumped. They used TotalView, and not knowing anything about it beforehand, they were quickly able to come to the resolution basically in less than a day that had stumped them for weeks. I think the original quote was like within hours. So this was doing a neural network simulation, and pretty awesome case study. That is available on the website as well. Anyways, here's the website. I actually did get through. Here's the website. I encourage you to visit, sign up for an evaluation copy of TotalView, documentation, videos, case studies, and all that. Feel free to email me. If you email me and ask for the slides, I'm happy to send them to you because I know I whipped through several of them. So unless you have a photographic memory, you didn't get everything that was on them. Feel free to ask. I'll be happy to send the slides and also talk to our sales guys. So thank you very much for your attention. Late in the day on one of the last days of the conference. But I guess I'll maybe have time to take questions or